And welcome MCV for you folks. This is our last lesson, our last day in Unit 2, and it's kind of a special day called implicit differentiation. Before we get to that, pretty good warm-up question. I hope you tried it. Um, it's a chain rule question. I'm actually going to show you a few ways to do this, hopefully fairly quickly, but um, whenever I say it's going to be fairly quickly, it ends up being a long, drawn-out process. So I apologize if this is going to go long, but here we go. Differentiate y equals u to the exponent v with respect to x, where u is this other function. There's a number of ways to approach this. It's kind of like anything else in our math. You know, when we know a sufficient amount of math, it feels like there's a number of ways to approach it and still get the same answer. Okay, so what this is saying, and notice this is the Leibniz version of the chain rule, although we'll see soon that we don't have to think of it that way. We want the derivative of y with respect to x. I hope you noticed that and read that. Um, and the chain rule says, well, if we want the derivative of y with respect to x, if that's what we want, well, we can take the derivative of y with respect to whatever independent variable it's defined in, u in this case, and then we take the derivative of u with respect to x at the end. And so it's just like two kind of derivatives back to back. And what this looks like, um, this looks nasty, I realize, but there's the kind of chaining part. That's kind of like the chain part. But we could do this sort of thing first. And again, remember, if I'm going too fast, you can pause. Well, the derivative of y with respect to u is easy peasy, right? If um, u is the independent variable, then this is one of the first derivatives we ever took. The 5 comes down, the 4 goes down, and then there's nothing on the end because the independent variable that we're taking the derivative with respect to is u. It kind of takes the place of x. And then du by dx is the derivative then of this function with respect to x now, where x is the independent variable. If x is the independent variable, well, this is just a quotient law, right? And hopefully I haven't goofed up any of the arithmetic here, but the derivative of the top, write down the bottom, subtract, write down the top, derivative of the bottom over the bottom squared, expand and tidy. And if I made any errors, maybe no, I think that's okay. And then to put it together, so this is the derivative of y with respect to u, that's this thing. This is this thing, and then I put it together, and there's that thing, there's that thing. Well, except for in this expression, I don't want any u's involved at all, so I take out the u, and I jam in what u is equal to, and then I get this function with respect to x instead of to u. Notice that if u is this thing, I've got that on the bottom, and hopefully I didn't goof on any of my arithmetic. If I did, you can make fun of me in class. A second way, and this is more of a like if you fear the Leibniz, you shouldn't fear the Leibniz, but if you fear the Leibniz, this is a kind of like a Newton way of thinking of this. We know the big function y is equal to u to the exponent 5. But if we wanted the derivative with respect to x, that means we're not sure about u then. It's like an inside function. So when I take the derivative of y, the 5 comes down, the 4 subtract 1 from 5, I get 4. But then since I don't know anything about u, I've got to write down the derivative of u prime. Since u is some function of x, we must take the derivative of the inside thing, and then I'd write u prime. Notice this is exactly the same as this, where this is the derivative of y, and then this is kind of like the same thing as u prime at x if we use the Newton notation, right? Use Newton notation, that's u prime. And in fact, this is where we're going today a little bit. I want to show you a third way, and this is okay that you do it this way. Probably it's more natural, and you fear this. We want to find y prime. One way is just to do the composition of functions, right? Good old grade 12 advanced functions, composition of functions. Write it as a function of write y as a function of x, then just take the derivative of this big thing. And this we're not that scared of. This is, we were taking the derivative of this quite some time ago, where we just have this inside function. This is the power of a function rule. The 5 comes down. And I know the inside thing has to, the g at x here has to stay the same. I'm going to write that down. And then I got to take the derivative of the inside thing. Now, the derivative of the inside thing is a big, long, nasty mess. It's a quotient rule, but you know, we're going to take the derivative of the top, write down the bottom, subtract, write down the top, derivative of the bottom, and this hopefully is looking over the bottom squared, and this is looking familiar. It's looking much like what we saw the earlier thing. Did I make a goof over here? Oh yeah, I did. Look at that. That's supposed to have a 4 on it. That was supposed to have a 4 on it. So there's actually 4 there and 2 there. There's a 6 in total. 6 in total. So here I got 5 and then 2x plus 5 to the exponent 4. I tidy all this up, and that was minus 9, I believe. And then on the bottom, I've got 4 of them there and 2 there. That makes 6 of them altogether. And then I think it's pretty much what I had before, I believe. Now that I fixed that up. Yes, I did fix that up. Fixed. All right, on to today's stuff. Last new stuff, and it's not really new stuff. It's the same stuff written in a different form. I guess that's new stuff. Hopefully you've got the note printed off, because there's a bunch of stuff there to look at and read. This is called implicit differentiation. Solve problems involving the derivative rules. So we know all the derivative rules we're going to need. This is just a different flavor. So we know f prime at a gives the slope of f at x equals a. So this is what we're used to. Right? We're used to taking the derivative and finding the slope of tangents of functions. But what about relations? Like this circle here isn't a function. You know, if I wanted to take the derivative of this and find slope of the tangents here, how would I do that? Well, as it turns out, it's not that hard at all. And it's got to do with this idea of this isn't a function, it's an implicitly defined relationship. And I think that's what it says next. And I think this is one of the examples we have to do, so I'm not going to say much more about that. It says because y is implicitly defined as a function of x, we use a process called implicit differentiation. So this idea, implicit is opposite of explicitly defined. Explicit means we would have y equals. And so your instinct might be, well, why don't I just take this and then get it in y equals? And don't write this down, it'll mess up your note, but if I wanted to explicitly define y squared, I might do something like this. And then take the square root, and I know when I take the square root, I've got 2 pieces, and that's why it's not a function, right? I get 2 pieces. One's that's the top half of the circle, that's the positive square root, and one that's the negative square root is the bottom of the circle. This is explicit. And I certainly could find those 2 tangents if I were to take the derivative of those 2 different functions, right? I've got 2 functions. One is this one, and one is this one, and I could take the derivative of either of them and find the slope that way. But if we're clever about this, it's not that hard. It says to find the derivative of an implicitly defined equation, it says differentiate both sides of the equation. Use the chain rule on y, and we'll see what this means in a second. So use the chain rule on y, and then solve for y prime. So this idea of, well, when it was y equals, and I took the derivative of both sides, the left-hand side was always y prime, and then the right-hand side was always where we did the work. But if there's stuff going on around y, well, we could still take the derivative with respect to the independent variable x. It's just that sometimes we might need to have a chain rule going on. And we'll see this. I think it's the first example. Given y squared plus x squared plus y squared equals 4, find y prime. So here we go. So I am just going to differentiate with respect to y. I'm just going to take the derivative with respect to x. So here, for instance, the derivative of the right-hand side is easy peasy in this case. The derivative of 4 is just 0, right? I take the derivative there. Now, if I take the derivative of this side, I see it's a sum rule. So I've got this. Then what's the derivative of this with respect to x? Well, that's just 2x. And what's the derivative of this with respect to x? Well, I see that this part is a function. It's kind of like this part here is a function of x that I don't know what it is. So here I use a chain rule. The 2 comes down in front. I write down the inside function, and then I take the derivative of the inside thing. The derivative of the inside thing I'm just going to write as y prime. I'm going to come back to an in-between step here that might help clarify this, but really I'm just taking the derivative. And now it says to solve for y prime. So that's going to go on the other side. And then I divide by 2y. Tidy up. And then I get an expression for the slope of the tangent at any point. And it's weird. It looks weird because the right-hand side involves both x's and y's, but don't be afraid. Don't be scared of this. Before I go on with B, one way that our Leibniz notation helps here, perhaps, is I could think of the derivative of this as this line here. I'm going to get rid of this just so I can have more room. If I take the derivative of this, and you're not writing this down, this is just to help you understand, I hope. If I want to take the derivative of this side, I'm taking the derivative of each of the pieces, and with respect to our independent variable x. Okay, the derivative of both sides. Clearly, I know that's true. This we've done 100 times. Now this, well, this is the chain rule, right? This is the idea I've got an inside function, y. Remember, since this it doesn't have an x in it, it's a function of y. We have to write the y prime on the outside. I could think of this as an f at x or a g at x. This is the chain rule right here. That's the chain rule. Okay, and that's one spot where I think the Leibniz notation has got an advantage because I can see that I'm taking the derivative with respect to the independent variable x, not u or not t or not y or some other variable. And hopefully that didn't confuse you anymore. Let's do B. Find the slope of the tangents when x equals 1. So I see here x equals 1, and I'm going to put in there x equals 1, but I don't know what y is equal to. Well, what was y equal to? Y was implicitly defined. Well, hang on. There it is right there. Y was implicitly defined in this equation right here. So if I put in x is 1, then y is, well, I'm going to have to do a little calculation. This is 1, subtract that from both sides, then I take the square root. I get 2 answers. I get plus 3 or y equals minus 3. So I'm going to get 2 answers. The slope is x is minus 1, y is square root of 3, rest all. You're right on the ball today. There. Or y prime equals negative 1 over the negative square root of 3. So that's tidied up. So does this make sense? Well, look back at our diagram. At x equals 1, different color here. You can mark up your diagram if you like. That's up to you. At x equals 1, I've got 2 tangents. One here. Could I convince you there that the y coordinate would be positive root 3, and then the slope is negative 1 over the square root of 3? I bet you I could convince you of that, right? Where down here, where x is 1, y is negative the square root of 3, and then the slope would be a positive number. Perfect. Makes sense. This calculation gave us both slopes at once. All right, Dandy, we're going to pick up example 2. Example 2, the last example? Can't be. No way. Last lesson of the unit be that short? There's a couple of examples, and there's some nice ones, so we'll pick that up in part 2.